Hello, today we're going to talk about the difference in software architecture between Mac OS, Linux, and Windows. Our group is conformed of Andrés Pérez Bonilla, Sergio Quiroz, Jerome Watson, and me, Alberto Matos Zúñiga.
First, it is important to refresh what is an operating system. By installing an operating system is a program that controls the execution of application programs and acts as an interface between applications and the computer hardware. The operating system is in charge to ensure the fulfillment of convenience, efficiency, and ability to evolve. Then, it is explained how Mac, Linux, and Windows architecture helps accomplish these objectives to facilitate, optimize, and extend the computer functions. Also, it is important to know the concept of an application program interface in order to understand the architectural components functioning. An application program interface is a layer of abstraction used to provide communication between two entities, the client and the server. Now, I'm going to explain you a little bit about Windows. The Microsoft Windows operating system has dominated the desktop computing market for the recent years. In 1985, Microsoft was initially named Windows. Later, it was replaced by a new version known as Windows NT, released in 1993. Windows has a modular architecture. Each function is handled by one component. The applications and other operating systems access through standard interfaces. It is possible to remove, upgrade, and replace any module without codifying the entire system again. Next. The kernel mode has the following components. First, the kernel. It commands the execution of the processors. The kernel manages process switching, thread scheduling, multiprocessor synchronization, and interrupt handling. Then we have the hardware abstraction layer. It isolates the operating system from platform-specific hardware difference by mapping between generic hardware commands and responses, and those unique to a specific platform. Then we have the executive. It contains the essential services such as threat management, security, memory management, and I/O devices. Then there is the windowing and graphic system. Implements the graphical user functions such as dealing with user interface controls, windows, and drawing. For the last, we have the device drivers. They are dynamic libraries that extend the functionality of the executive. Next. The Windows Executive Modules components for specific systems functions provides an API for user mode software. Here we have the I/O Manager. It provides a framework through which I/O devices are accessible to programs. Cache Manager improves the performance of file-based I/O by causing recently referenced file data to reside main memory for quick access. Then we have the Virtual Memory Manager. It controls the memory management hardware and data structures which map virtual addresses, manages physical memory, the paging files on disk, and virtual addresses. Then we have the Object Manager. Manages Windows executive objects that are used to represent resources. Then we have the LPC facility. This is Advanced Local Procedure Call. Implements cross-process procedure call mechanisms for communication between local processes, implementing services, and subsystems. Then we have the Power Manager. Manages the power energy among various devices and can be configured to reduce consumption. Then we have the plug and play manager. It selects the drivers which are required to support a specific device and loads those drivers. Then we have the security reference monitor, validates access and functions as a generation rules auditor. Then we have the process thread manager, manages processes and threads. For the last, we have the configuration manager. It implements and manages the registry. This is the repository for system-wide and per user settings of various parameters. Next. Now it is important to explain a little bit about the client-server model. The Windows structure is designed to support applications written for multiple operating systems. This is because Windows provides this support using a common set of kernel mode components under the system layers. For an application designed for a different operating systems to run in Windows, it is just required to recompile it. Because the interface is the same, it is not necessary to modify the code. Windows implements this model. This architecture can be adopted for use internally to a single system. There are some advantages of using a client-server model. The first one is it improves reliability. The second one is it provides a suitable base for distributed computing. And the last one is that it simplifies the executive. Next.
The Linux operating system started out as Unix variant from the IBM PC with Intel 90386 architecture. Since its launch, many people started collaborating over the internet the development of the operating system because Linux is free and the source code is available. Today, Linux is a full-featured Unix system that runs on multiple platforms such as Intel Pentium and Itanium. One of the keys of the great success of Linux is the availability of free software package following the Free Software Foundation that is called FSF auspicious. Linux doesn't use microkernel. It is structured as a compilation of modules that have the ability to load and unload on demand. These independent blocks are called loadable modules. Next. The Linux loadable modules have two important features. Dynamic linking, that is a kernel module that can be loaded and linked into the kernel while the kernel is already in memory and executing. Stackable modules. The modules are filed in a hierarchy. The module tables includes the element. Next, there is a pointer to the following module. Name, pointer to the module name. Size, module size in memory pages. Flags, module flags. NSIMS, number of exported symbols. NDIPS, number of reference modules. SIMS, pointer to the modules. DEPS, pointer to list of modules that are referred by this module. And refs, that is a pointer to a list of modules that is in the module. Next. Kernel components. The figure shows some process running on the top of the kernel, and each box indicates a separate process, while each curly line with the arrowhead represents a thread of execution. That's because in Linux there is no distinction between the concept of process and threads. The kernel components are signals used to call into a process, system calls, process requests a specific kernel service, process and scheduler, creates, schedules, and manage process, virtual memory that allocates and manages virtual memory from process, file systems, provides namespaces from files and directories and provides file system function, network protocols, support the sockets interface to users, character device drivers, that manage device that requires the kernel to send or receive data on byte at a time, block device drivers, manipulates devices that read and write data in blocks, networks device drivers that controls network interfaces cards and communication ports that connect to network devices. Traps and faults. Manage traps and faults generated by the processor. Physical memory. that controls the pool of page frames in a real memory and allocates pages from virtual memories. Interrupts, manipulates interrupts from tangential devices. Next. The Linux V service. The Linux V server is an open source, fast, lightweight way to implement a virtual machine on a Linux server, and only a single copy of the Linux kernel is involved. The V server consists of a reality modest modification to the kernel plus a small set of OS user tools, and it supports a number of separate virtual servers. Next.
macOS. Apple Inc. was founded by Steve Jobs and Steve Wozniak in California in 1971. Named after Jobs' return from an apple farm, he said the name was fun, spirited, and not intimidating. macOS was first introduced by the company in 1984 to run on the Macintosh line of personal computers. Focused on the intuitive ease of use, unlike all the other contemporary PCs, it was graphically based. There were no commands or paths. Users needed a mouse pointer to navigate through it. In 2001, Apple rolled out Mac OS, which was a major redesign for the OS. It ran a Unix kernel and offered a memory protection and multitasking. It also provided its Finder, which was a new elegant-looking interface called Aqua and a dock bar. Functionally, the Mac OS architecture consists of layers shown in the figure. The base layer is the Unix core, called Darwin. Up on the next layer is the graphics subsystem, which consists of three parts, which are Quartz, OpenGL, and QuickTime. Next is the application layer. It has four components, which are Classic, Carbon, Cocoa, and Java. And the top layer is for the user interface, called Aqua. The core OS is called Darwin. Darwin Core is based on the Berkeley Software Distribution, BSD, which is a version of Unix. The heart of it is called Mac. It performs the fundamental task data flow in and from the CPU memory use. Its major features are the following. It has a protected memory, which provides a separate memory area where every application can run, keeping it in its own memory space so it does not affect other applications. So if any application crashes or hangs, the other applications are not affected. In previous versions of macOS, they did not have a protected memory. When one application crashed, it took down other applications or the OS itself. It has an automatic memory management. It manages the random access memory, the RAM, by itself, and it automatically allocates RAM to the application needing it. It has preemptive multitasking. Under macOS, the operating system controls the processes the processor is performing to ensure that every process has the resources it needs and that this processor is used efficiently. This to ensure the performance for background and foreground processes. In contrast to the cooperative multitasking used in previous versions of macOS, where the application had to fight against themselves for the resources needed. As a result, when applications couldn't get the resources needed, it resulted in instability and poor performance for the applications that could not grab the resources they needed. So if a process was moved to the background, it is stopped. It has an advanced virtual memory. The Mac core uses a virtual memory system that is always on, so it can manage the virtual memory efficiently. So that memory is only used to ensure maximum performance. In previous macOS versions, you had to control how virtual memory was used manually, making it less efficient whenever it was on. It would cause the performance of some applications to slow even if you had plenty of RAM. The Darwin core also provides input and output services for macOS X. It supports three key characteristics of modern devices: plug and play, hot swapping, and power management. It also supports several file systems under macOS through its virtual file system, VFS, such as the macOS standard format, HFS, which is the standard standard for the macOS versions prior to macOS 8, the UFS standard file system for Unix systems, and the UDF. This is the universal disk format used for DVD volumes, and the ISO 9660 standard for CD-ROMs. Darwin also supports major network file protocols. It supports Apple File Protocol, AFP over IP client. macOS X uses bundles. A bundle is a directory containing a set of files that provide services. A bundle contains executable files and the resources associated with the executables. The two types of bundles are the following. The applications, with these bundles are designed as file packages so the user sees only the files he needs to work with. The rest of the resources might be hidden from the user, and this makes installing applications simple. And the framework. The framework bundle is similar to an application bundle, except that it provides services shared across the OS. Frameworks are system resources. Frameworks contain a dynamic shared library, so this means that different areas of the OS can access the services provided by the framework. Frameworks are always available for the application and services running in the system, and they are not provided as file packages, so the user sees them as individual files that make up the framework. As I said, macOS is a Unix architecture. There are a lot of file name extensions under macOS than there were on the previous versions of the OS. It includes an advanced graphics subsystem with three main components, which are Quartz Extreme, which is part of the graphics system that handles 2D graphics. It provides the interface, graphics, fonts, and other 2D elements of the system. OpenGL, which provides the subsystem with 3D processing for 3D applications. It is an industry standard, so it is also used on Windows and Unix systems. The macOS implementation of OpenGL provides many 3D graphics functions. This makes OpenGL work in a better way under macOS than any other OS running it. And QuickTime, it provides support for digital media, such as digital video. It provides the enabler of video and audio streaming under macOS. It also enables the view of applications such as QuickTime Player and creative applications. It is also an industry standard, so the macOS can be seen on Windows and other computer platforms as well. Finally, under the interface, we have three environments in the application system. The classic environment, which enables Mac to run applications that were written for older versions of the OS. They do not benefit from Mac OS X advanced features such as protected memory by other classic applications, and the environment can be affected when a classic application has problems. The Carbon environment also allows developers to port existing applications to use Carbon application program interfaces. The process of porting a classic application to the Carbon environment is called carbonizing. The environment offers the benefits of Darwin for carbonized applications, such as protected memory and preemptive multitasking. Carbonizing means less work than developing an application from scratch. The Cocoa environment offers a state-of-art object-oriented application development environment. These are applications designed for Mac OS, and most take the advantages of Mac OS X. Finally, the Java environment enables users to run Java applications, including pure Java applications and Java applets. Java applications are widely used on the web because they enable the same set of code to be executed on various applications.
Now we can talk about the overall difference between the operative system that we have talked about. As we can acknowledge, there's multiple differences between these systems operatives, but punto, we can see how there are certain functions that every operative system manages differently, like the file structure, which the way that they manage the files differs slightly between the operative systems. Windows follows the directory structure to store different kinds of files for the user. It has folders predetermined, like documents and images, and all of these can be stored in new folders, which can be created. The structure in macOS is accommodated through directories, where the root directories is the main one. As for Linux, it's quite different to the other operative systems because it stores all the information as trees. As for the registry, a Windows registry at its base is a master database, which stores all the settings of the computer. The registry has an editor that allows to view keys, values, and drivers. Linux does not have a registry of its own. The settings are stored on program basis under different users in the hierarchy format. There is not centralized database for storing these details. For the command terminal, Windows has a terminal with it, which is used to execute commands called Windows Command Processor. A Mac provides a console with a command line, prompt, and terminal. Linux also has its terminal and it has a shell prompt, which the difference is it defines the terminal and how it will behave and look when running. As for the kernels, that's the main difference between the operative system. The key difference between Linux and Windows is the type of kernel that it uses. Linux kernel is mostly monolithic, while Windows microkernel is microkernel, while macOS is a hybrid between both of them, called X and U, which means not. Both kernels may differ one another. In the microkernel, the host services and kernel are separated, while in the monolithic, this does not happen. In microkernel failure, in one component will not affect the other components, while in the monolithic it does. Microkernel is easier to add new functionalities, and microkernels are smaller than monolithic. So in fact, there's some difference between the kernels of Mac, Linux, and Windows. Next. So we can have some conclusion that not every operative system works the same way. Each has its own architecture and a specific way to function. Operative systems doesn't have the same functionalities of each other, and maybe the operative systems are better in some tasks that the other are not. And their specifications are they should be better in the tasks that they're doing, like macOS for media, for example.
The users should know the differences between each system to make sure to select the one that accommodates to their needs. You won't need a Windows computer, for example, to use media, as Alberto said. And finally, the file system and the registry and the command terminal are the main architectural differences, though there are plenty of differences which should be analyzed before acquiring one of these systems. Thank you.